So it's 12 bits. I think 80% of the guys made it right. No, actually not really anything. This one, a lot of you just directly put this number over here, but for the value to be placed in this counter register, you need to use this one to minus this guy. That's the only minor issue I found. Okay, but other than that, not a big deal here. Oh, this one you have to shift it to the right first and assign to the higher byte, and then the lower byte will, by default, will take the lower byte and put it into the L register. Okay, not too many issues. Any questions on anything? A lot of stress on tutorial 5. Did you get the first task done at least? How many of you? No? Okay. I'll probably just directly give you the solution for task 1, so you can create task tools, ISRs. How is that? So let's take a look at it. Task 1. If you look at the code, you can find out it's just so simple, because all these functional blocks are being used repetitively. You can see. So declare all these ones. Okay, I hope this is not a big problem. If you look at the tutorial, this is a major figure you want to look at. Okay, so OC5B is the output of the PWM module, right? So that one is shorted to PL4, and so this JPA, you can see JPA is a connector on the board, and you can easily locate it because the next to it is a speaker's connector. So this is a little 2 pin headers that you want to short it. So if you short these two by using a little jumper, and it will short pin 45 to the input of the base of the BJT transistor. Okay, it's a switch. So the PWM waves from this OC5B pin, which is a timer 5's PWM module, when you program it, will directly being sent to here. Okay, and that one turns on and off this transistors like a switch, right? So the current can go through this or not go through it, in the same pattern as your digital signal over here, and so create pulses to blink this IR emitter to create that 38 kHz IR emission. Okay, and that one goes to the air and being received by the decoder. Decoder's output is pin 44, and you should find out pin 44 over here. Okay, and you put a female to female connector and short these 2 pins. So the output of the decoder will directly be fed into the RX pin of the 01. So UR1's modules RX will be taken by that. So that's a hardware connection. Okay, so when you know the hardware, you want to code it up accordingly over here. So the IR LED pin should be 45 because that's the emitter's output pin. And that's the value we calculated. That's for OCR5B because that defines the 10%, right? It defines the 10% of the duty value, which is according to this guy. So OCR5B. Okay. We calculated. We got 420. So we use 10% of 420 for the on time. Okay. That's why we want to use 42 for that number. And initially, you give a letter 5 as the first letter to be sent, and every time you press S, it added increment 1 to the letter. So if you add a 1 to a character, it's actually adding an ASCII code to adding a 1 to its ASCII code. Okay, to the byte. So if you have character letter 5 as the first one to be sent, every time you send it at the end of the send case, you add a 1 to a letter. it's adding to that character, it's actually adding to its ASCII code. So it's adding to the byte. So so next time you press S again, it's actually sending 6 instead of 5. And that is why we have the case here, and you can see I have a letter plus plus over here. Okay? Every time you send it, you do a letter plus plus. So for the S case, let's get into the setup first. So for setup, also for this one, right before the setup, you don't have to create a list, since we basically were just using numbers. I don't think we used this list. If you don't have to, if you just want to put a number there, which is fine, because all these ones are giving you different ball rates, right? So to let you select it. But if you just directly put that number into TCNT3, it wouldn't make any difference. So what I'm saying is here, right? So for this one, remember task 1 we used 1200, right? 1200 is for the selection we selected 1, so which is this guy. So this number will give you the timer 3's count to be 1200 bits per second. Am I losing anyone? Okay, it's recorded. If you don't understand this, you'll be deep in trouble. So this is fundamentals we have been talking about for 2 weeks, and these will be exactly on quizzes. If I find out we need a quiz, and definitely will be on the final exam. Okay, make sure you understand these basics. If you find out what I'm talking about over here, that totally doesn't make any sense to you, go back to watch the video and visit during our office hours. Definitely understand it. Okay, we should speak the same language. Okay. So in setup, definitely for the IR pin, which is pin 45, you set it up as output. That's usually you have to do at the very beginning for the setup pin. And for the serial 9600, that's for the serial monitor, the USB 0, right? The UR0 module. And for UR1, which is the RX pin, that is pin 19, right? Pin 19, that's RX1. And that's taking the data at 1200 bits per second. And at the very beginning, you need to clear all these registers because we are using timer 5 and timer 3. Timer 5 is used for PWM, and timer 3 is used for creating the 1200 bits per second envelope. And like I said in the class, we need to clear timer 3's overflow bit before you get into the loop. That's just required. If you don't do it, you're getting an error message. That's for my when I debug it, I find it out. So you just directly do it. And ICR5 is based on the calculation to create that which frequency? ICR5 is creating which frequency? This will get you. So I am losing everyone. 38K, right? What is this register holding? It's the top. That's the top of the PWM, right? Okay. So it gets into the loop. It's detecting the command that you are sending to it. So first you want to send it, right? When you are sending it, the first bit is definitely a 0 bit. It's the starting bit, right? So if you want to send a 0 bit, you want to turn on the PWM, because whenever it's on, the decoder will receive a 0. So it's pulling it down to start the UR communication. So how to turn it on? I already showed you guys in the tutorial, right? To turn it on, you have to follow these steps exactly. If you are not using SRs, you have to exactly doing the same thing as what I'm showing here. There might be some minor changes if you can still make it work, but most of the time it doesn't work. So you want to turn on the PWM, you have to do 1, 2, 3 lines. Okay, so the PWM is on, And then you immediately turn on the timer to create that time delay, which is 1 over 1200 second. Okay? How to turn on the timer? Assign a value to timer 3, TCNT3, turn on the timer. While it's not overflowing yet, wait here, and once it overflows, jumps out and stop the timer. And once you stop the timer, you clear the overflow bit. These are all the steps you have to follow. And these are given on the website, okay? You just follow. You turn on the PWM, create the time delay, done. That's the stop bit. Okay? And then we move on, move forward with the data bits. So the data bits are, we know it's 8 bits, and we are using a mask to detect every single bit starting from the LSB. So that's why the mask is all zeros with the ones. So it's 8 bits over here in the mask. So while the mask is not 0, which means that little 1 here is not being shifted out to the very left hand side yet, right? So still in the middle. Because whenever that little 1 is being shifted out to the left, the mask becomes 0, right? And that's the end of the transmission of the data bits. So we want to turn it off over here. Am I losing anybody over here at this point? So this is the technique we use to detect and send every single bit in the data bits, in the data byte, okay? So if it's already shifted out, so while it's not being shifted out, and then we want to check it, right? If we are detecting that bit in that byte, the data byte, if it's a 1, we turn it off, okay? If it's a 1, we turn the PWM off. So it's outputting a 1 at the decoder. If it detects the 0, we turn on the PWM so it pulls it down to 0. So it doesn't matter which one is being selected through the conditions. We always want to shift that mask to the left by 1 bit. So next time, that little 1 will be shifted, will detecting the another bit in the byte. Okay. No matter which one is being selected, we want to turn on the timer immediately. Okay, because that's to make that duration. And then after all these are done, okay, we want to do the stop bit, which is a 1. Okay. If you want to turn on, if you want to put up at the decoder's output, you want to turn off that PWM and create the duration right after it. That's it. That's all the 10 bits. And eventually you add a 1 to the ladder, okay, to the character, which is adding that 1 to the ASCII code of the character. So next time it's gonna send a 6 instead of 5. So for receiving, like I said, the RX module is not receiving because you press R. It's already being already received before you press R, right? Because whenever you press this S, all the 10 bits are in the air, it's out of control. And after, so the way that works is the receiving module, even though you are not using your own customized ISR for UR receiving, but the UR receiving module does use ISR by itself, even though you don't have the ISR written by itself. Does that make sense? Task 1, we don't have ISR for UR1's receiving module. There's no receiving modules ISR written by itself. However, you are using this read and also this one here to check it. But everything running behind the scenes, actually, the UR receiving module does use ISR by itself. Okay? It's by default. It uses ISR to receive it. So now let's come back. Okay? Just relax, come back. So the data 10 bits are being sent. Once you press S, everything will be executed. and all the 10 bits starting with a pull down 0 starting bit, right? 0, and with all the byte, and then pull up. So the 10 bits will be in the air, and then the decoder will receive it. Okay? Is the receiving module of the UR will start receiving that 10 bits, or it has to wait for the R press event? It will start receiving, okay? And so the interrupt will be triggered when everything is received. So which means when it pulls it down, because hardware physically the decoder's output is shorted to RX, right? RX1. So when the data comes in, it starts receiving, like starting from starting bit being put down, then start pumping every single bit in, boom, 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 will start coming into the RX module, okay? Once all the 8 bits are being received, and it will be stored in the buffer in the RX module, and it's going to trigger that UR receiving interrupt, and so you can read from that. So over here, if something is being received and this one becomes available, that means the UR will be triggered as a ISR receiving interrupt will be triggered, even though you are not writing it by yourself, but behind the scene it's being received, and this will become 1, right? And then this is getting satisfied. It comes in, you read it. Okay, you read from the buffer. You read from the buffer. So for this method, if you can see, we use different ways to read it. It's the most common way. I can say it's a beginner's way. If you find a middle schooler or high schooler, they can do this job as well. It's no, because they don't have to learn logic in order to understand what's going on. They just directly check this condition and then read from it. Okay? And that's everything in our case. That's it. Done. That's everything about task 1. Okay? So you see the pattern over here for task 2. You set up everything, and remember the way to turn on and turn off PWM could be slightly different. Maybe turn off the same, but turn on is different if you're using ISR. You don't have to, redo everything by yourself. I think it's just this part, right? Just turn on this part. That's it. If you're using ISR, you press the S. It only turns on the flag. Only turns on the flag. And then you receive every single bit in the ISR instead. Okay? That's what you are going to do. It's going to be in the ISR. So all the S, you see what I'm doing here for the S, should be placed in the ISR and should be modified a little bit and put in ISR. Okay? So you press S, there's nothing else to be done. You just put give a true to a flag. You can name the flag whatever you want. Just transmission to be true, and then whenever it interrupts, it will detect the flag and get into the idle and jump to the next state. All right. So get task 1 done first and gain some confidence, and move on to task 2. Okay. Like I said, you should be challenged. It's a computer engineering major. It's not a business major. You are supposed to be challenged. If I'm giving you a hard time, you should appreciate that. Don't want to make it too easy. It's okay. After this, you will, get a job. You're happy. That's a goal. All right. Another thing, I can let you know the plan for the following semester. I deleted one task, which is the DDS one, which is very important, but I just don't have time for the semester. So let's delete it. So we have tutorial 5 right now you guys are working on. I'm going to wrap up task 3 today. And also the in-class number 10 will go through the state diagrams for that. And then Friday this week, I'm going to talk about ADC, sampling, very important topic. ADCs, microphones. I already created task 1 for you guys, and task 2 is on the way. Working pretty hard as well. You You don't have weekends. I don't have weekends as well. So it's a really interesting project because you couldn't imagine that you're whistling. If you whistle, your whistling is a sound wave. See here? That's my whistling. I digitize it using an ADC.
Or if you can't whistle.
Huh? If you can whistle, I provided you with the option over here. Just turn on the YouTube videos. There's the audio over there. You can turn on that one. This is actually the one from the YouTube, but mine is very similar to this. You know, it's almost a sound wave.
Do it.
Hmm?
Do it.
I mean, just regular whistle. Just regular whistle. It's a sound wave. You don't have to make it special.
I said do it.
It's a sound wave. Couldn't believe that, right? It's very similar. Sometimes there will be an offside, but it's very similar to a sound wave. So it's a really fun project to do.
Actually, can you go back to the first file you had?
First, what?
Like the text file you had a little bit ago,
Uh-huh.
the task one.
Yeah. For what?
The text file you were showing.
Oh, the text file. I'm gonna send it to Canvas. Okay.
Today.
Yeah, yeah. For PCB, right? For the project, you can see the task from Canvas. We'll start talking about that today, right? And Wednesday we'll talk about this as well. We can see the goal is not to make a super complicated project. The goal is to let you guys work through the whole workflow. So building microcontroller system on PCB and order the parts and solder the PCB and test it and make a functioning system. So you guys can put it on resume and even talk about that during the interview. It's a really important skill to have. So in that case, we cannot do everything, right? We cannot do everything. So I would rather keep the coding and project circuit design itself simple, but eventually get a functioning board. So I highly recommend that you guys just grab, since we're having several different modules on our Skyboard, right? The IR, speaker, microphone, SD card, we're going to cover that. And the LED, the RGB LED, right? So all these modules. So you just have to use two of the modules, two of the 5 or 6 modules, and find out these modules, peripherals, the circuits from the Skyboard, and put on your customized PCB, okay? And then your code, you can imagine, because all these modules we have already covered in the tutorials. So your code or your projects will be very similar to whatever our tutorials are. So it can make things a little bit easier, okay? But you have to write a proposal on a project, and it's one of the tasks. It's deliverables. I think it's over here, right? It's 100 points for the proposal, but just one page. It's an easy point to get to earn. It's an easy credit to earn. So write a one-page proposal. Just simply tell me what you want to do, what you are planning to do. All right, and usually I will be able to tell if you can really get it done or not, since I have all this kind of experience, and then I will give you some feedback for that assignment, so we can start working on it. Just keep in mind that it doesn't have to be super complicated. I hope that you guys eventually have a functioning PCB, customize the PCB instead of having a super complicated project. Okay. So even though this is a little bit intimidating, but eventually it's not that difficult. Okay.
What do you mean by duplicate the Skyboard schematic?
Yeah, that's a training about PCB, about learning how to do PCBs. Okay.
Okay, so with task 1.1 due on Friday, that's following the schematic in
Yeah,
the tutorial you gave and not our custom.
No, just this one.
Okay.
Here, that's the link here. Could be a bit intense, okay, but it's easy. Just trust me. So there will be, we can probably push it to Sunday, but let me see here. See, we have Wednesday. Wednesday have nothing but working on the PCB on the course project, the task 1.1. So install Eagle today as soon as possible, and start exploring that Tuesday and Wednesday, and when we're meeting on Wednesday, I hope I can just directly answer questions instead of just helping you install Eagle. That will be, wasting your time. So, okay. Hunter already went through everything, right? But is that very difficult? It's not, right?
Yeah.
You get everything done in 2 days, 3 days? Or
Yeah.
what? Yeah. So I'm giving you guys, what's that?
So we're doing the same as the skyboard, but then we're doing another board for our project. We're doing 2 boards.
Yeah, so the thing is you have to be familiar with whatever the parts are on the skyboard. Give me a second, let me turn this on. So you see that you have first one, which is schematic over here, right? This is the I don't have time to create a new tutorial for you guys, but this is the one I taught at Mines last year, and this is a really good schematic to follow. So follow this one, eventually build this one. Will teach you how to use Eagle to create a schematic. And the reason that I want you guys to follow this one is because for the op-amps, it has 4 op-amps inside, right? So it's another consideration. And just some tricks over there. So just follow this one so you understand how to, add a frame in there and add the power parts and everything. Okay, follow it. And then for self-defined libraries, is this one. It's self-defined libraries. So you are creating individual parts and placed in here. So maybe not 100%. I'm saying not everything. For example, the switches like this one, we're not going to use. But what I want to see is after following all the schematics, you are able to create a schematic very similar to whatever I shows in the tutorial. Okay, if you are saying, hey, I'm missing one part, missing one of these ones, it probably doesn't really matter. So keep in mind the goal is to let you guys learn how to use Eagle and create a decent schematic and layout during a very short period of time. So if you don't follow this procedure, your schematic and layout may be very ugly and maybe not showing the following the good practice of general engineering design in electrical engineering. So that's why I highly recommend that you follow these tutorials, even though these are not perfect, but it's pretty standard way to do it. And for the third one is the layout, okay, for layout. So for laying out the PCB, you want to manually draw the traces instead of using auto routing, because the auto router just creating a super ugly PCB. But you can see this example over here from one of the students at Mines. He spent 8 hours to manually lay out everything by hand. Okay, so this is a very good example of doing that.
I don't even think you can auto route on the free version.
You should be able to.
You
Yeah.
can't. Not on the one that I got.
Yeah, sure. I've been doing this a lot of times, but you only auto route whenever you have to. You know what I mean? So for example, all these ones, you can manually route it. You just manually route it. If you cannot, eventually, you can also auto route it. You can see this is the one I auto routed. You can see it's compared to the previous one. It's just not that nice. Okay. I did manually route these ones and these ones a little bit, but it's running out of space. The auto router is trying to drill a lot of holes, and which will make your PCB soldering and has a lot of issues. Can fill the PCB sometimes as well. And you can see the footprint is significantly larger than the previous one. It's the same circuit, and has a lot of blue wires. The blue traces are the traces at the bottom of the PCB. And if you manually route it, you can keep everything on the top. So the red traces are on the top metal. So you don't have to drill holes and route at the bottom. But I'm not asking guys to do the same as this one. It's unnecessary. But I've been showing a good example. Okay? But what you want to do is try to manually route as much as possible. And that's what I told Kai to do. And that's why you are seeing a manual layout of the skyboard like this. So all these traces are manually routed. There's no way if you run with the auto router, it will be a mess. But for this kind of PCB, you can tell that there's no way that I can manually route everything and keep all the traces on the top metal without drilling holes and having blue traces. It's too dense. Okay, so you have to drill holes and place traces to the bottom. However, it looks very complicated, but I think we probably should change this assignment a little bit. We should probably change this a little bit. So you don't have to duplicate the whole thing. That will be too much. I think just, the thing is you have to do a proposal first. But, this and next week, you don't know what you want to do yet, right? So that's the issue. Right. So.
I was thinking it might be more efficient if we just did the proposal first and then just followed these tutorials and made our decisions.
Yeah, another thing is if you haven't done IR yet and ADC and SD card, you don't understand what's going on over there, how to propose a decent project, right? You don't even know how SPI works. Yeah. So that's why I want to do the proposal after we finish the last tutorial, which is this one. It's not too far from now. It's just the end of next week, I think. So at least you understand what's going on, even though you are not finishing that tutorial, but you know what's going on, what's available on the board, right? So you can propose the project.
Why didn't you move this homework up? Why didn't you move this homework up?
Yeah, I mean, you need ADC as well, right? You know these. All right, let's probably follow this procedure. And so in your final project PCB, it definitely won't be this much or this many components on it. If you're only using two modules, you can get rid of a lot of things and just pick the ones you need. And also, we are not creating a PCB that you can program, okay? So you verify everything on your Skyboard, and then you know it's gonna work. And then you pick the parts, design the PCB, and directly just solder it, okay? And test it. So your final PCB won't be programmable. So don't need a USB. It's a product, right? It's a product. So you cannot imagine a product has a big fat USB on it to let people to program it. You can never see that as a commercial product, right? Since the products are not usually programmable. So you don't have a USB on it, so that's why, and so you don't need that USB to serial converter, which is the most difficult one to solder, which is a good thing. And so test everything on the Skyboard, and if you need it, you grab a breadboard and make the connections. And also, I recommend that you use two of the modules from the Skyboard, but you don't have to. If you think you want to use a display module, you want to use the accelerometer, you want to use a different sensor, you put in the proposal, and we'll look at it and prove it. Okay? If it's reasonable, I'm going to prove it. I'll give you some feedback. You revise it, then I prove it. Okay? And the final exam takes 10%. Midterm exam takes 10%. You're probably thinking, hey, you were at A, right? And you screw up your midterm, you are still at A. It's only 10%, that's why, right? But the final project is 30%, okay? I care very less about exams. I care about projects. That's how you can get a job, all right? So that's why it's 30%. If you fail this one, you're probably, at a risk of failing this class. So, the PCB ones over here, 400 points. You can see there's 200 points, 200 points. So if you finish all the PCB tasks, you're getting 50% of the project. Okay? Not too bad. And then the software, hardware verification follows the general engineering, embedded systems engineering process. You verify everything on the demo board. You have a Skyboard as a demo board. You verify everything on it, including the traces, connections. If you don't have the connections on the skyboard, you need a wires and a breadboard and place the sensor you want to use for project on breadboard and make the connections and program it, test it. And once it works, you'll start designing your PCB. Since you see that all the connections on the breadboard, these are everything I need for the PCB to make it work. Then you start designing the hardware, okay, on PCB. So task 2.1 is a proposal, and task 2.2 is the verification on the skyboard. So if you don't have a functioning PCB, you are getting 400 points here and 200 points is right at 60%. Oh, 80%. No. Like 70% or so. So you are getting 100 points for the proposal and 100 points for your verification on the skyboard. Okay? If you know what you want to do for the project and get everything functioning on the skyboard, you're receiving 600 points out of 800 points of the whole project. Okay? So for the first time designers and beginners for the PCB design, very likely your PCB eventually will not work. So you are still getting 600 points out of 800 points. And you'll probably receive some partial credits from here as well, okay? So don't have to worry too much about it. However, why I'm still giving 100 points for the PCB, because eventually what I'm looking at is a functioning PCB. If your PCB is not functioning, it's reasonable that I'm taking 100 points off, right? That's the whole point. Yes, there's a risk. As a beginner, maybe my PCB won't work. But you need to know that that's the important thing you want to achieve. And if you're not getting that functioning, you are losing that 100 points. Maybe there will be some partial credits, but I don't know yet. Okay? So you can see schematic manual layout, it's 100 points. And soldering, programming, testing, that's due after the day after the final exam. You can definitely turn it in earlier than that, but I want to give you more time to work on it. Eventually get a functioning one. So you might get a chance to get a second PCB. I will be able to fund it, but you have to do a soldering, testing, and find out the issues as soon as possible. I'm not going to do more than 2 PCBs for each of you, but hopefully you can get a first one functioning. And because we only have 15 students, that's a benefit of having a small class. I will be able to look at your PCB. If it pass the DRC, and usually 90% chance it will work. So I will work with you, sit next to you, and look at your PCB and schematic and layout and approve your PCB before I send it out for fabrication. Okay? Question?
Yes. You're saying everything on the design is due on the 14th?
No, this is the Gerber file of the PCB.
Yeah.
Yeah.
But is it the last day before break? I thought we had another day before break.
I didn't check that. Let me see.
Yeah, so should it...
No, it's a week before the break. Here.
What are we doing in that week then? After we turned in our PCB to you?
You work on the verification. Oh, programming verification is due before that, right? So probably you wanna verify it first, and then you design your PCB. So I have to follow that order, okay?
So what
And then after that, there's another task over here. This one due 17th, which is here. So I have 2 more days. Probably I'll push this deadline to here. Okay. Okay.
Okay.
That makes sense.
Yeah.
And then it takes 10 days to receive it. So I send it out. Takes 10 days, and I'm thinking probably I'll receive it during the break, maybe. So come back and start working on it. So I have 12 days to solder and test it. 12 days. It's a long time. You'll have several modules on it. Not everything on the skyboard, right? It's just 2 modules. So it should be a lot easier, a lot smaller board, and a lot easier to solder. Questions on the project or inputs on it? Okay. For the PCB design part, I think we will cover some tips, but I hope you guys can, install Eagle and make it ready before the Wednesday class. And Wednesday we don't have a lecture here, but it will be in that lab. So I hope you guys can start doing this, either today or tomorrow. So I will just, troubleshoot for you on Wednesday. It could be for this one, or could for the second one as well. Okay. And for task 1 and 2 for tutorial 5, 1 will be given, and 2, I'll give you a template to make it easier. Okay. So I have the time to work on the PCB. And for task 3, which is the in clocks number 10. In clocks number 10. The diagram, say diagram. I didn't bring it. I'll give you a template for task 3 as well. Okay, later. I didn't bring it. Definitely. Let's start from here. So keep in mind that UART has to be set up. The registers has to be set up in the setup function, which is this part. This is in the setup function. And remember, it's a 2400 bits per second. So we are using a different value, bulk value. Okay, you have to calculate it. And starting from M, it's a message. You press M, and you start typing. Okay, start typing. So you have to be able to see whatever you just typed. And here's the case M. It's handling all these events or operations. So you press M. These 2 lines will be printed out to let the user to type their message. And you can see these are out of control because it will directly being executed. And one is the transmit source address. Another one is the transmit destination address. And remember, I told you guys these 2 addresses are fake addresses. It's just for good practice. In the future, some of the other communication protocols probably requires addresses bytes. So we have this to be 1, this to be 255. They are just fake addresses. It's just 2 bytes you automatically placed at location 0 and 1, right? So you can see in the transmit IR buffer, I placed 2 addresses over here, 1 and 2. So put the 2 addresses over there at the very beginning. Okay? And the checksum, right? Checksum is addition of all these bytes, including the address bytes. So the first address, I put it into the checksum, okay, as addition. And for the following ones, I'm just keep adding to this summation result, this variable here. You can see. So the destination, and then I add a destination address to the checksum, the summation here as well. So it's start adding to itself. So if I have a data, you can see I have a data here. I'm also adding a data to the checksum as well. It's a data bytes, address bytes, including everything. I just keep adding to that same variable. so I can check for errors. And you can see I type I'm, it will do this, like kind of like initialize the message's first 2 bytes for you. And then you'll stay here, because if it's not receiving anything, it's waiting, okay, waiting. So it's basically like you press M, it's gonna wait for the user to start typing, okay? Before type anything, we will just wait here, okay, just wait here. And then if someone just starts typing the first letter, it'll jump out from this while loop and assign the index to 2, because you already have the first 2 letters as addresses. So you should start the data bit, the first data letter should be placed at the 3rd location, which is index number 2, right? So immediately give a 2 to I, and then start getting into this while loop. So see, this while loop has two conditions, and the second one is to trying to control it, so it's not exceeding the length limit of the buffer. We'll take a look at the picture after this. But the first one is the command receiving, right? So the command being received, if it's not the enter key, because trying to detect the enter key, whenever the user finishes the typing of the message, it presses the enter key in order to finish it, okay? So as long as the user is not pressing that enter key, I want to keep doing whatever inside the while loop. If it press it, it jumps out, which means the message, the data message, or the message body itself is done. And then I want to place the now over there to end it, to end the string, and then place the checksum at the very end of the message. So you can see here, right? So source address, destination address, commands, whatever message the user is typing, and then whenever the user press enter, it jumps out, and then you place this little now to the end of the string. So it's very useful. I'll let you guys know why, maybe on Wednesday. And then immediately you place the checksum, which is summation for error check, right after this guy, okay, to form the whole message to be sent. So here, place the now, place the checksum. And for the middle, right, the reason that it can see whatever it just typed in there is because you are printing this out. Only because you are printing this out. And definitely you don't want do not change the line, because all the letters are following the previous letters. And you assign the command, whatever you put in the transmit IR buffer, because these are the commands or data letters to be sent. And every time you assign to it, your index moves to the next one. So next time it enters here, it comes back to this line. It directly putting that letter to the next location, right? And immediately you add that command to the checksum. If someone typed a super long message, it just print out something, right? Print out something. So this one, after everything is being typed, it waits here for another letter. So you press 1, it does everything here, and then wait here for the second type. Wait here. If you type one more time, it jumps out and comes back to the top of the while loop. Okay, it's given. It just needs to understand it. It's given. And for the S, I think we'll start talking about that on Wednesday as well. Really quick. Couldn't cover everything, but Wednesday seems like we need to do the PCB, and also we need to wrap up this one as well at the same time. Okay. I will create a template. So this there's already a template for it. There's no internet connection, but I'm gonna add more things to the template so you guys can get started easily. Well, any questions? Anything? No? So there will be a lot of stress in the recent weeks, but after that, it's basically just we don't have new lectures, right? So this is the tutorial 5, we have tutorial 6 and tutorial 7, then we're done. So all the rest of the semester will be just focused on the course project. Okay, not too much. All right.
What about in class 10?
In class tonight, maybe Wednesday or Friday. I don't know yet, but maybe Wednesday. Okay.